A couple more, looking on the left at the cities that are within 200 miles of an interstate highway. Again, that's going to depend upon what is your definition of city. Interstate highway is pretty well defined, but what constitutes a city and where are they? And we probably are not seeing all of them in this data set. Again, there are quite a few cities that exist that are not being shown at this particular scale. So on the left, selecting cities within counties named Washington. So again, there are going to be far more cities than is being shown on the map. And some of the cities that are actually selected we can't see because we're zoomed so far out, those points are coalescing together. So other things to bear in mind. And the scale is very important, and definitions of things are very important. So does your data set actually work for what you're interested in? If I was interested in knowing information about cities, just by looking at these two examples here, I know that the data set that was being used here is probably not complete, and that I would need to find something else, another source of information, another data set somewhere that was more complete. Recall from earlier lectures that information in our data sets quite often is generalized, and that can create problems and issues when we're considering looking at things at different scales, and whether our information, again, actually is being truthful, precise, and accurate as to locations of features in space. So let's take that idea from a previous slide of thinking about cities that intersect or are close to rivers. So let's make it an intersection. If we want to select all of the cities that intersect a river, and we know that there are a lot of cities that exist right on the banks of a river, so we should get returns back from those. When we're zoomed out, like the little graphic in the upper right, if we're zoomed out, it appears, well, yeah, there's a lot of cities that seem to be right on the river. But remember, scale applies here, and the line feature is actually probably not that big. The point location is definitely not that big on the Earth's surface. So let's zoom in on the left and take a satellite image, superimpose over it two city point locations and the line that is supposed to describe the river. And we can see that although the city, and in fact maybe two or more cities in this area are indeed on the banks of the river, the point location that for some reason is showing us where the city is located is where the cartographer chose to place the idea of a city center. Definitely not on the river. And the river itself, the line that describes it, is similar to what's there in space, but it's definitely not truthful. It's not accurate and precise. It's close to the path of the river, but it's not exact enough for use. And so think about the digitizing issues. When someone may have created this or these data sets, if they did them manually, they're placing dots where they're guessing the city is located. They're perhaps tracing the outline or the line of the river using an image that's zoomed back out further, some satellite image, for example. And so those errors creep into our analysis, right? So someone's digitization process doesn't really work for us for this kind of analysis. So just bear in mind, scale is always something we need to consider when we look at data sets. And when we are querying them, know that the scale at which the data sets were created is going to inherently affect the results that you get, the records that are selected, whatever kind of query you're building, whether it's a table-based SQL statement or a spatial query. So directly related to scale and digitization issues. Those link right back into the idea of topology and logical consistency, whether or not the information in your data set matches what we know to be true on the ground or something that's supposed to be true legally. So for an example here, we've got South Dakota and Nebraska, and two counties in South Dakota, Shannon and Bennett, and the Pine Ridge Indian Reservation, which is a federal entity. Now, these different spatial features should share boundaries. Now, it could be that we're looking at data sets that have different datums and projection systems. We could be looking at data sets that have exactly the same datums and projections, but someone created the data wrong. And probably no matter what we do, we won't be able to get those things to line up properly. There are errors in the data sets, and in this case, let's presume the worst, that these are the same datum, same projection, same coordinate system, and they don't match up. So you've got a fundamental fatal flaw that all of your analysis that you're doing that uses these spatial entities will be flawed. So the thing to do is you discard the information and go find perhaps more recent information, but more accurate, more precise, more truthful data sets to make sure that your analysis does not carry those flaws forward. Another form of spatial query are the extraction functions, clip and erase. And these are kind of powerful little tools that we can use. And what we see are a couple graphics below demonstrating the clip and erase functions. So we have a target data set, which is represented by the rectangles. We've got a source data set, which is going to be what actually performs the spatial query. And then we have results. So on the top, we've got a rectangle. We apply the clip function using the circular data set, and by default, it's going to pick the maximum boundary of the clipping function. And so this works just like a cookie cutter and pops out information from the original data set that is all within the clipping data set. So again, cookie cutter, there it is. Erase is going to do something similar. You have the input rectangle. We've got then the erase function being the same circular data set, but instead of punching out the cookie, what we're doing is we're leaving behind the dough. So we erase where the cookie is supposed to be on that data set. So you can imagine these are both very powerful things. The clip function you could use if you need to separate out a study area. The erase function you can use if you need to exclude something from the study and just eliminate it from consideration completely. So examples of this might be if we're interested in creating a buffer zone around a stream where we're going to exclude logging within 500 meters of a stream. So we can clip out the stream using that, using a buffer created at 500 meters around the stream, and then we clip it, and we've got that zone. If we want to study that stream further, then we've got all the data that are just around the stream from the data sets. Erasing might be, for example, if you're doing some sort of a study on federal lands like Forest Service lands or BLM, Bureau of Land Management lands, and there's private property over which you don't have jurisdiction or is doing something completely different, so you want to exclude that from your study, you can use the erase function to erase those polygons out of the land management data set. So if we imagine a hypothetical city with two different data sets, roads and land use. If we have roads being our input data set and land use being the clip or erase data set, the clip will keep the features within the boundary. So the cookie cutter will cut out all of the roads within the land use polygon. Erase would get rid of all of those roads within the polygon and preserve all of the roads outside of the polygon's boundary. Okay, so just another example of differences between clip and erase. So by default, clip and erase are going to use the maximum boundary of the polygon set that you use as either the clip or erase data set. So in this case, we see above a complex set of polygons describing an urban area. If you use clip or erase, it's going to ignore all the internal geometry. It's going to use just the external boundary of that entire polygon set, and that will be what's used for the clip or erase function. An important thing to note here about using clipping and erasing and other types of geoprocessing is that if you're working in shapefiles or you're working in geodatabases, there's a real fundamental difference between them. Geodatabases store vector data as feature classes or feature classes within feature data sets. Geodatabases will automatically update the shape length and shape area fields within vector data sets. Okay, that's really important. That's really crucial. That's something really handy. If you're using shapefiles, you have to do that manually. You have to update those columns in your output data set manually by right-clicking on it and saying calculate geometry. So geodatabases, here's another plus in the column of whether I want to use them or not. Geodatabases will assist you if you're conducting analysis that involves changing lengths and areas of vector data sets. You're better off putting them within geodatabases because those two entries, the really crucial ones, shape length and shape area, are going to be updated for you when you do the geoprocessing routines. So something that we can do is kind of a neat little trick. You can tell ArcGIS to do kind of on-the-fly clipping, but it's not really clipping. It's kind of like applying a window to the data. So you can say, here's a layer that I might choose to clip my data sets with, maybe the boundary of a study area. But maybe you really don't want to actually clip the data sets, but you visually want that effect. So what you can do is apply this on-the-fly clipping routine within the options for the view within ArcMap or ArcScene, ArcGlobe. And what it'll do is just restrict the visual properties of all your data sets to that study area. So visually it's going to look like you clipped them all, but mechanically you didn't touch the data sets at all. They're still fine, they're intact, they're just being displayed basically through that polygon data set, kind of like as if it's a window that you're peering in, and the only thing you can see is what's in the window. You can't see the rest of the house. And so that's something that you set in the data frame as a data frame property. You say, here's a layer to use or a data set to use for this on-the-fly clipping routine. So how do you do that? You go into the data frame properties menu and the data frame tab. You say, I want to clip to a shape. You specify the shape, the vector data set, and then voila, it does it. So below you see examples of several different vector data sets being displayed at the same time. And we're using a clipping layer, looks like watersheds, 2B, whatever that is, and applying it to the data frame, and it clips out visually everything else that's there. It doesn't actually affect your data at all. It's just saying only display this portion of the data. So very handy if you need to leave your data sets alone, but you only want to display certain things within a particular map project. This is the way to do it. Another variant of spatial queries is the map overlay. There's a couple different versions of that. What a map overlay does here in this example is we're splitting features in one data set based on another. So we have land use, polygons, and roads. And so what we can do is we can say form or use the operation to apply the attributes of the polygons, land use, to the line features, the roads. And so basically we can combine those two tables together, and the table information from the polygon layer gets sucked into the line layer, and we split the lines at the borders of the polygons so that each line segment has the attributes of the polygon that it's sitting on top of. So that's why it's called a map overlay, a map overlay procedure. We overlay these two different vector data sets, and we're able to combine the information from those two. Okay, so kind of a powerful thing to be able to take information from one data set and add it into another data set, even if they're not the same geometry. So here is an example of that very thing. We use the lines over the polygons. We associate and link those things together through the table. So the resulting data set we're calling here roads LU, signifying that it was the roads layer, and we combined all of the attributes from the land use data set into the new data set. And so the result coming out is lines that contain the information that was in the land use table. So the road names here, what is a street or a road, the land use ID code, or the land use ID as one column, excuse me, and the land use code as another column. So it's kind of a neat trick to be able to do that if we need to examine characteristics of different road segments or any other linear feature or point features. You can think about the possibilities that you can do with that. It's pretty neat to be able to do that with this map overlay. We're combining information from totally different sources. So the things we can do with this idea of an overlay: point in polygon, line in polygon, or polygon on polygon. So the point in polygon overlay we use to assign polygon attributes to points. So here each point on the map is a house, and within school districts. So we can, if we needed to, for some reason, we could pull all the education statistics for that district, apply it to each house in the data set, and then if buyers are interested in comparing schools, meaning people that are interested in buying a home, they could click on the individual home point and get the information related to the school district from that. You think, why wouldn't they just click on the school district by itself? Well, if they know the address of the house and they pick it out of the database, and your database is set up in order to let people view it as a house location, then you're just pulling the information in and you're making it easier for people to use in their interactive websites.